Good afternoon, everyone. In this video, we're going to go through and work through the screening example that we're going to do in class. We just want to have you have this video here as a reference to go back through and recreate some of the steps if you lose track of things down the road. So the data that we're going to be using in this example, we're going to be looking at the unique effect of pain severity, opiate use, and post-traumatic stress disorder on overall role functioning in a sample of individuals who've been exposed to motor vehicle trauma. So up here we have our variables. We have a PTSD variable, an continuous indicator of severity ranging from 0 to 136, an indicator of pain ranging from 0 to 6. We've got opiate use. This is going to be a dichotomous indicator, just a yes-no variable, no meaning no use, one saying yes in terms of use. And then we've got a role functioning variable. This is going to be our outcome ranging from 0 to 100, with higher scores going to indicate greater levels of overall functioning. So our model down here is regressing functioning onto pain, opiate use, and PTSD. And what we're going to do in this video is going to go through and work on basic screening procedures of looking through this. So the standard multiple regression screening with the exercise regression data set, this is what we're going to be using here. Okay, so first thing that we're going to do, just like we do with all of our analyses, first thing I want to do is take a look at accuracy, plausibility, missing data. So in SPSS, it's pretty easy. So I'm going to go through and just, lock this down here. All right. There we go. Okay. Sorry about that. So what I'm going to do is I'm just going to right-click and sort. And remember that in SPSS, anything that is missing data is going to get sorted up to the top. And it looks like we're fine here, so we don't have any missing data. I want to go through and note that. So what I've got is, at least conceptually, I have 3 continuous variables: pain, PTSD, and role functioning. And then I know that my opiate use is going to be a dichotomous variable. So what I want to do is I'm first going to start by going Analyze, Descriptives, Frequencies. I'm going to look at my opiate use. Okay, I'm just going to go through, paste that here. I'll create a syntax file. I cannot stress how important it will be to have a syntax file that you set up. You don't want to have to walk through all these steps each and every time you do one of these screenings. So the degree to which you can get a syntax file set up with notes, here we'll say checking something like that, so that you know what's going on. This will make your life much, much easier down the road. Okay, so I'm going to go through and take a look at my opiate use. So again, no, yes, pretty even split on this variable, nothing out of bounds, so that we see for opiate use our values are plausible, no missing data, we check that, and for this variable, a pretty even split across people who are using medications who aren't, so we're pretty excited about that situation. Okay, so I'm going to go through, going to go to descriptives, and now I'm going to look at my variables that I'm thinking as more continuous. So I have continuous pain severity score, I have my continuous PTSD score, and then my role functioning variable. Okay, so I'm going to go through and I'm going to save standardized values. So this is going to give me Z scores. Then I'm going to go to options. I'm going to request skew and kurtosis values, continue there, and then I'm going to paste. Okay, so we'll run through those data, and this is going to give me my my table here. And so what I want to do is, I know there's no missing values because I checked that, but I want to check plausibility first. Right? So if I pull up my sheet here, I can see that and I guess we'll just work from the sheet. I know that PTSD should range from 0 to 136, 0 to 111, so we know that those are all in bounds. Pain 0 to 6, 0 to 6 there, and then my role functioning 0 to 100, 0 to 100 there. So I know that all my data are within bounds. So no missing data. All my values appear to be plausible and reasonable given my known measurements. And so we can check those boxes in terms of our screening. Okay. Other thing we want to do here is take a look at our indices of skew and kurtosis. Remember that what we're looking at is the absolute magnitude of these indices, with values less than or equal to 2 being reasonable guidelines for stuff that might sort of be considered at least not problematic violations from normality. So if I'm looking at here, I got a skew value of negative 0.7, so some negative skew. Kurtosis looks fine though. For my PTSD scores, very little skew, almost no skew, very little kurtosis. That looks fine. But if I take a look at my role functioning variable, see, it looks like I have pretty prominent positive skew in terms of role functioning. I'm also seeing quite a bit of positive kurtosis. Remember that positive kurtosis is going to be kind of that peaked type of thing. So in terms of things that I'm concerned about, pain and PTSD, at least based on my indices, are looking reasonable, but might have some concerns with role functioning. So I'm going to go through and want to take a closer look with that. So what we're going to do is we're going to go up to Analyze, and we're going to Descriptive Statistics and Explore. What we want to do is we want to say, all right, give me pain severity, PTSD, and role functioning. Okay, and I want it to label cases by participant number. Make sure that you've got that set up. And then for plots, I'm going to request histograms here. Okay. So I think that should do it. I'll paste this in, go through and run this. All right. So we can go right down to my graphs because that's really what I want to take a look at. When I take a look here, again, my pain scores didn't look like they were anything I was going to be too concerned about, but pain's looking okay. We have some kind of strange gaps in this. We go through and we sort our pain variable here. Okay, so it looks like these are calculated in 0.3 intervals, which is probably why we're getting getting some of these gaps here. But so this is looking not too bad. If I go down through and I take a look at my box plot, again, things aren't looking too terrible. I've got 1, 2, 3, 4, 5 scores, maybe 5 scores exceeding 1.5 times interquartile range. But for the most part, so I want to make note of those. But for the most part, I'm not too worried about what's going on with pain. Okay, my PTSD score, that looks beautiful. That looks fantastic. A really nice symmetrical distribution here. Nothing much to note. Again, we've got one case, 221, person right out there, someone with very, very high PTSD scores. But again, with a sample of 201, we're going to expect to have some scores that are fairly high. So, given the distance away from the rest of the distribution and the size of the sample, not too worried probably about that person having much of an impact on my overall results. Okay, but now we go down to role functioning. This was the variable that we thought we may have some concerns with. Okay, and we do see that what we've got here is actually, our histogram is telling us we don't actually have a continuous variable with role functioning. It looks like what we have is an ordered categorical variable. Okay, So we've got a lot of skew. We've got a huge disproportionate number of people reporting 0, meaning that people are reporting very, very low levels of functioning, which makes some sense given that this is a help-seeking survivor or a help-seeking sample of individuals who are seeking assistance with pain, PTSD following accidents. So we're seeing most people reporting very little functioning, and then a small percentage of people out here in a tail. So we're seeing that. Remember that we saw evidence of some prominent positive skew, and then some problems with our kurtosis value, a value of 4, and we're seeing that being that kind of peaked with this kind of flat tail coming out. So we're going to note that we probably have some concerns there. Again, if we go through and we take a look and sort our role functioning variable, we'll see that we actually have just 5 values: 0, 25, 50, 75, 100, right? So what we really have, don't really have a continuous variable. We've got an ordered categorical variable. And if I go down, I take a look at my box plot, this is also terrible. We see that my median, my first quartile, and my third quartile are all 0s, and any value that's not 0 is identified as an extreme value exceeding 1.5 times or over 3 times the inner quartile range, which if my inner quartile range is 0, then anything that's not 0 is going to stack up here. So we've got some problems. Pain looks okay, PTSD looks okay, but my role functioning variable, and that's my outcome, I'm having some concerns about this, okay? So what I might decide to do is I might want to go through and maybe see what happens if I transform this variable, okay? So what I'm going to do is I'm going to go up. Now remember that this is a variable that ranges from 0 to 100, okay? What I might want to do is I might want to see what happens if I log transform this variable. So if I go to transform and I go down to compute variable, what I can do is I can name this new variable role ln. I'm going to say role ln is going to be equal to, and if I go to my arithmetic functions here and I find ln, this is my natural log. So if I double click that, and then so it wants me to know I want to take the natural log of role functioning, okay? Now I could run this, right? But what's going to happen is I'm not going to get an answer for the majority of my sample, because we know we can't take the log or natural log of 0. So what I'm going to do is I'm going to say I want to get the natural log of role functioning plus 1. And what this is going to do is it's going to add 1 to all my cases. So my minimum value will be 1, my max value is 101, and then I can take the natural log of those data, okay? So I'm going to paste this, right? And so this is, and again, you can make notes and would encourage you to, we'll say transform variable due to evidence of skew, something like that, okay? Just so, trust me, you'll thank yourself down the road when you go back through, and it's easier to figure out what you've done because you've gone through and made notes in your syntax file. Okay. So I'm going to go through and I'm going to create my role functioning variable, and then what I'm going to do is I'm going to run descriptives on this. So I'm just going to copy my descriptive statement here and paste in this natural log variable that I'm gonna run here. Okay. So again, this is just an example of how things are sometimes easier to work from the syntax file when you're working on things. So I'm going to highlight this and create my role functioning variable, okay, or the natural log of my role functioning. So here is my natural log of role functioning plus the constant of 1. And so now what I'm going to do, I'm going to run through, I'm going to run my descriptives. When I run my descriptives, I'm going to see that relative to role functioning up here, we have a skew of 2.3, kurtosis of 4.2. Here, my skew is improved, right? I'm down to about 1.5 in terms of positive skew. My kurtosis has gone way down, and so I might be excited because what it looks like is I've improved at least the skew and kurtosis indices for this variable. Okay, so let's plot it. Let's see what's going on when we take a look at our actual box plots in our histogram. So again, I'm just going to copy my examine command here, and then just going to paste in the natural log of row functioning. Again, just taking a shortcut so I'm not working everything through the drop-down menu here. If I do this, it's still not great, right? So I'm seeing what this natural log function has done is it's pulled in my tails. So I don't have quite sort of what I've got going on here. Now my range is somewhere between 0 to a little less than 5. But what you'll notice is if I look at this, I've got 1, 2, 3, 4, 5 variables, 5 values in my raw data, because again, we identified this, my rule functioning variable as actually ordered categorical. If I go through and take it the log transform, it's still ordered categorical, right? I only have 5 values. I'm only taking the natural log of 5 different values, which is still going to give me 5 different values. So we still have everybody still stacked up here with values of increasing functioning, but at least it's brought it in. It's a little bit better than it was. But again, if I go down through and I take a look at my box plot, still my first quartile, my median, and my third quartile are all equal to 0. Anything that's not 0 is all still stacked up here. So again, what we've done is we've improved the distribution a little bit. It's not as severe as it was in terms of overall magnitude of skew and kurtosis, but the transform didn't fix the variable. The transform didn't make this categorical variable turn into a continuous variable. It didn't make it normal. It's still not great. Okay, and just as a preview, this is going to be probably the biggest limitation of these data if we were to want to run an actual regression model with this. In actual fact, what we'd probably do if this was an actual study is we'd want to take a step back and think about maybe using a different model, one that accounts for categorical outcomes instead of trying to run this through a standard multiple regression. Okay, but we are going to proceed with our transform variable as our outcome. But what you'll see as we go through and we look at our residuals and other types of plots, we'll see this continue to pop up as an issue and start to impact some of our graphs and figures that we're seeing. Okay. So to this point, we've gone through, we've assessed missing data, accuracy, plausibility, univariate distributions. Now what we want to do is we want to go through and take a look at our z-scores. Okay. So what I'm going to do, and so again, we're looking for here extreme values within these individual distributions. So I'm going to go back to Analyze, Descriptive Statistics, Descriptives, and now I'm going to go down through, get rid of those, and I'm going to instead look at descriptives for my z-score of pain, my z-scores for PTSD total score, and then my z-score for the natural log of row functioning, because we decided that this was going to be the variable that we're going to use in terms of our outcome. We're going to use that transform variable. Okay, so I'm going to turn off my standardized values. Under options, I don't need to look at skew and kurtosis, right? Skew and kurtosis of a z transform is going to be exactly as the skew and kurtosis of my raw variable. Standardization isn't going to change the shape of the distribution at all. Okay, so we're going to go through. We're going to hit paste. Go through and run this. All right, and remember what we're looking for here are values that are going to be quite large, both in the positive and the negative direction. All right, and again, for a sample of this size, things that might start to register as something we might be looking at or notable are going to be cases that with standardized scores in excess of 3 standard deviations above or below the mean, or about 3.3 z-score plus or minus 3.3. 3.29 is going to roughly correspond to a p-value of 0.001. So, but again, with a sample of this size, particularly clinical sample, we're expecting some values to be large. But if we look here, we actually don't see too much of a problem in terms of cases that are going to be clear, influential, extreme values. For our pain variable, minimum score, we've got a score, someone's scoring about 3 standard deviations below the mean, max only about a standard deviation and a half above, so that's looking okay. Max z-score for PTSD total is about 3 standard deviations above the mean, about 2.6 below. That seems fine. For the natural log of my role functioning variable, we've got people who are 2 1/3 above the standard deviation, or 2 1/3 standard deviations above the mean, half standard deviation below. So in terms of our overall z-scores here, we're not too concerned about any extreme values. Again, what we'd be concerned about here are things that are very, very large and have the potential to start dragging my mean values around with stuff. But here, we're looking like we're doing pretty good. Okay, so at this point, we've gone through pretty much steps that we've gone through with our means-based analyses, looking at missing data, plausibility, and univariate distributions in terms of skew, kurtosis, and then extreme values. Okay. Now for our regressions, what we're going to do now is we're going to go through, and what we want to start doing is taking a look at our bivariate plots. Remember that when we run regression in an applied setting, we are 99.999% of the time going to be violating that fixed effects assumption of a regression, right? Our predictors aren't fixed variables. Our predictors are variables that we collected that just kind of come in, so they're random variables. And so we always violate that fixed effects assumption, but we can ignore that fixed effects assumption so long as our data are multivariate normal. And we're going to assume that our data are multivariate normal if all of our univariate distributions are not demonstrating severe violations of normality, and our bivariate associations between our variables are linear and homoscedastic. Okay, so what we need to do is we need to take a look at bivariate plots. So what I'm going to do is I'm going to go to graphs, go to chart builder, and what I'm going to do is I'm going to choose scatter, and I'll pull this up here. Okay, so again, scatter dot plot, and we take this little scatter matrix, and what I'm going to look at is I'm going to go through. I'm first going to enter my natural log of my role functioning, and then what I'll do is I'll look at pain, PTSD, and this is going to be a little bit different than what you have in your handout, but I'm going to include opiate use in there too. What we're going to do with this plot is we're going to assess for linearity and homoscedasticity. We can't have nonlinear relations with dichotomous variables, but what we can start to do maybe is start to see if we've got problems with violations of homoscedasticity. Homogeneity of variance is what we called it with our means-based analysis, so I'm going to drop that down there as well. Okay, so I'm going to go through, paste this, and so this gives me a giant syntax or command structure here. But I'm not going to worry about this. I might like say evaluating bivariate relations or something like that. Okay. And so what I'm going to do is I'm going to go through and I'm going to run this. Okay. Now, SPSS is going to give you a graph that this in and of itself is not terribly informative, okay? But what I can do is I can double click on this, and what I can do, so I've double clicked on this. It's going to give me a chart size. Let me see if this what I do. 460. Okay, so that just makes that chart a little bit bigger, something that's a little bit more conducive to us taking a look at. So again, I just double clicked that. Oops, and that chart value came up here. I'll do this again just to make sure that we run this chart, right? It's kind of small. If you double click, there we go. If we go chart size, and you enter 460, hit apply, and close. That just makes this chart a lot bigger, which will be nice for us to go through and take a look at. Okay, so we made the chart bigger here. What I'm also going to do is I don't like these open circles, so I'm going to double click on that, and I'm going to see my marker thing come up, right? So what I'm going to do is I'm going to go through size and hit 3. I'm going to tell SPSS to fill these as little red dots, and I'm going to hit apply there. Okay, and close. And so now what we see is kind of improved our things. We got a little bit more precise dots. And then what I'm going to go I'm going to go through to options, and I'm going, or let me see, elements. I'm going to go to elements, and I'm going to say fit line at total. Okay, what this is going to do, and I get to sort of go through, make sure I have a linear model there. This is going to give me a regression line through each one of these plots. Okay, that can be helpful. And then if I want to go to options, I want to hit show charts in diagonal. This is going to go through and it's going to give me histograms for all of my variables across this diagonal. And so what I'm going to do is now I'm going to exit out, and we'll see something that actually ends up being kind of useful in terms of looking at bivariate plots. Okay, so what we want to do here is we want to assess whether or not we have evidence for nonlinearity or violations of homoscedasticity within these data. Okay, so if I'm looking at this here, I've got my role functioning, my pain scores, my PTSD scores, and this is opiate use. Okay, with opiate use, this is a dichotomous variable, so really all I'm going to be looking at here is to see whether or not we have much more variability at one level for one group than another. So this is going to be people who are not using opiates. These are going to be people who are using opiates. What we wouldn't want to see is maybe if in people who aren't using opiates, pain severity was all sort of stacked down there, so none of this was up here. So we have just a small range of variability at no opiates, but then a ton of pain severity at people who are using opiates, something like that. But thinking about this in terms of homogeneity of variance kind of on this. But with our opiate stuff, it's not looking too bad, so we're not too concerned about that. Right? Now, when we're looking at our continuous variables, what we're wanting to look for is whether or not we have evidence for nonlinearity in our data, or violations of homoscedasticity. Okay. Now, I'm not seeing anything that's clearly looking like a nonlinear association between any of these variables. Okay. Now, this regression line is just plotted. This is just the best fit regression, but I'm not seeing any non-normality or nonlinear associations here. Other thing I want to do is look at for potential violations of homoscedasticity. Okay. And really, I don't see anything that's terribly concerning, but maybe what I do is here, let's say I'm looking at the association of role functioning and say PTSD total score. Now maybe if I'm looking at this, I'm saying, okay, at high levels of role functioning, PTSD is not super variable, right? It's here versus at low levels of functioning, whole range of PTSD scores. Now, remember that our concern, we want to see something that's severe violation of homoscedasticity is going to be something that is about 3 times the variability at its largest point than the smallest point. That's probably about half the variability at the smallest point relative to the largest point. But let's say that I did want to go through and take a look a little bit further at this particular association. So what I could do is I could go up to Graph, go back to Chart Builder, okay? But this time I just want to straight up scatter plot here. I want to make sure that I get the same plot, so I'm going to take the natural log of, whoops, that's a z-score, natural log of row functioning, put that in my x-axis, PTSD total in my y, and then hit OK there. All right, and so really, this doesn't look like it's anything too bad going on. Again, I can go through, double click, and play around with the features in my graph a little bit. So I can say apply that, close, go to elements, fit line at total, and click off attach label and apply, close. Okay. So really not anything too severe here, but if you see anything in your scatter plot matrix that you might want to take a closer look at, this is what we would go through and do. Okay, so in terms of our bivariate associations, again, for our violations of fixed x assumption, again, what we have is some evidence of nonlinearity, well, not nonlinear, non-normality, violations of normality with my row functioning variable even after I transformed it. That's my biggest concern. But within this scatter plot, I'm not seeing clear evidence of severe violations of homoscedasticity. I'm not seeing evidence of non-normality, and so that's a good thing. Again, my biggest concern is going to be the distribution of my outcome variable here and the level of measurement. Okay, so to this point, we've gone through and done all the stuff that we can do directly with our observed variables. What we're going to do now is we're going to go through and we're going to take a look at our residuals. Remember that in our regression screening, most of our primary assumptions have to do with the residuals. Okay, so what we're going to do is we're going to request a regression model from SPSS. We're going to run a regression model. We really don't care about the regression model and the coefficients in it. We're just running this to go through and get residuals so that we can go through and take a look and see if we can find any problematic violations. So what I'm going to do is I'm going to go to Analyze, and I'm going to go to Regression. We're going to go to Linear. I'm going to select my log transform on my row functioning as my dependent variable. Then in terms of my predictors, I'm going to indicate opiate use first, so that's going to be my dichotomous variable. Then I'm going to enter my pain variable and PTSD. Okay, so this is giving my model I'm regressing row functioning onto opiate use, pain, and PTSD severity here. Okay, then I'm going to go to statistics, and I'm going to request collinearity diagnostics, and I'm going to ask for some case-wise diagnostics here as well. Okay, we can go through and play around with outliers and things like that, but we'll just leave it there. So again, click collinearity diagnostics, case-wise diagnostics, and hit continue. Okay, then I'm going to go hit plots. What I want to do for my plots is I want my z of my predicted value, my standardized z values. I'm going to put that in my x-axis, and then my standardized residuals is, my SD residuals. These are going to be my externally studentized residuals, which we talked about in class. I'm going to drop that in my y variable here. Okay, so what I've got is I'm going to plot my predicted variables and my standardized or my externally studentized residuals in my y. Then I'm going to hit histogram, normal probability plot, okay, and then I am going to hit continue, okay. Then I'm going to go to save, and under save I'm going to ask Stata to save me some variables. We're going to request our leverage variables, or excuse me, my leverage values, and I'm going to ask for my studentized deleted residuals, and I'm going to ask for cooks, okay? So remember from class, our studentized deleted residuals, these are going to be residuals that are corresponding to roughly corresponding to a t-distribution, so these are the types of, lots of different types of residuals. This is the one we're going to ask for. Leverage values is our measure of leverage. Leverages are leverages. So this is our influence, or our measure. Our studentized deleted residual is our measure of discrepancy. This is going to be our measure of influence or leverage, and cooks is what we're going to request in terms of influence statistics here. Okay. And so I'm going to hit continue there, and that pretty much does it. So I'm going to go through and I'm going to hit paste. Okay. Here is residual analysis. Okay. And so again, what I'm going to do is I'm going to run this model, and this model is going to give me a bunch of statistics that I'm then going to go through and taking a look for at the distribution of my residuals. Looking at discrepancies, leverages, influence, things like that. Okay. I'm going to go through, run my model, and so the results of the regression I'm going to ignore for right now because I really don't care about them. Right? What I am concerned about, first I'm going to go down to my scatter plot here of my standardized predicted values and my studentized deleted residuals. This looks like a pretty terrible plot, but I'm going to go through and do some things to just kind of fix it up a little bit. Again, I don't like those open dots, so that's just my preference, but I'm going to go through and do that. I'm going to hit that, okay? And then what I'm going to do, I don't know, we'll make it bigger just so we can kind of see stuff that's going on. Okay. And then what I'm going to do is I'm going to go options, y-axis reference line. Okay. And what I want to do is I want to just get a reference line. Remember that with our residuals, our mean residual value is going to be 0. But what we want to see in terms of the distribution, we're wanting to look for linearity and then the normal and homoscedastic distribution of our residuals. And so I'm going to request a SPSS give me a y line or a y reference point at 0. I'm going to hit apply. And what SPSS did is it gave me just a reference point right here at 0, so I can look at things above and below. Okay. And then what I'm going to do is I'm going to go to elements, and I'm going to say fit line at total. But this time, instead of getting a linear regression, I'm going to ask for a lowest. Okay. And I'm going to unclick attach label because I don't want it to do that. And I'm going to hit OK. And so what we've got here is this lowest function is just a smooth measure of fit that's going to attach to this. And so it's not necessarily a straight function, but it'll just give us a sense for whether or not we have potential nonlinearity here. Okay, so I'm going to hit close. I'm going to close that. All right. So if this is my residual plot, this is not what I would want to see. Remember that for our residual plots, going back to class, I want to see something that looks kind of like this. Here's my 0 line, and then I've got a nice distribution above and below with most of my values centered around, my residuals centered right around here on that midline, but then with things increasingly up and down here, okay? That's not what I'm seeing at all here. What I've got are these lines that sort of run straight down. We've got very clear things going on. What's going on? Remember that our outcome variable is not actually continuous. My measurement can't take on any value between 0 and 100 in the raw score. There's only 5 possible values that it can have. And because there's only 5 possible values my dependent variable can take, this is why we're getting this 1, 2, 3, 4, 5 lines here, okay? Again, remember that our residuals are estimated as my observed value subtracted from my expected value. So these are all values for the natural log of rho functioning, where the observed value was larger than what the expected value is by the model. Anything down here, these are all values that were my model is expecting larger natural log of rho functioning than what we're seeing here. And so what we're seeing, and again, this lowest is doing something that looks very weird and strange. It's kind of following down here and coming up. So it's not looking great. And note that in your handout, it'll look a little bit different because we're using updated, or I'm using a little bit older version of SPSS here. What we're wanting to check with this plot is we're wanting to look at linearity, right? Seeing if we have any clear evidence of nonlinearity in our data. And then we're going to look at the normality of the distribution and any violations of homogeneity of variance. So we're doing 3 things with this plot. Here, it looks like, if I were to just glance at it, that I might have nonlinearity, but I'm thinking what's going on with this lowest is it's more of a function of my measurement, my level of measurement, than anything else. And so really, I don't know that I'm seeing clear evidence of nonlinearity here. Again, that would be something that looks, kind of like that, or something that was kind of like that. This is wonky, but I think this is an artifact of the measurement and not actually anything that's going on in the data necessarily. So I'm going to carefully set aside my concern about nonlinearity of my residuals. Okay. I'm going to also then want to take a look in thinking about the distribution of my residuals. Here, I might start to be a little bit worried. It looks like everything's kind of stacked up on this line with fewer values running up top, right? Again, if we have skewed residuals or non-normal residuals, oftentimes this is what it'll look like. So we've got our midline and most things are kind of stacked around here. And then when we miss in one direction versus the other. It looks like we could have some issues here where our residuals tend to skew maybe positive a little bit. So I might have some concerns about whether or not I've gotten our normal, the distribution of my residuals are not normal. But I'm going to go through and sort of hold off on that for maybe right now. I'm going to look at a couple of different graphs for that. Other thing I really want to take a look at here, and one of the prime things, is looking at violations of homoscedasticity. Okay, again, what we hope for with these plots is something that looks like across all of my expected values of y, the distribution of my errors are pretty even, right? This would be something where we'd have evidence of homoscedasticity versus something here where we see an increasing spread of my residuals around my midline of 0 as my predicted values of y increase. Okay? Again, because we've got a wonky outcome, this is kind of hard to read. Here we don't have any variability in my residuals, but that's because everybody's kind of stacked up there. Here, yeah, I don't know. It's hard to tell really what's going on with this. So I don't know that I would say I have a clear problem with heteroscedasticity here. Again, I'm thinking what's going on is this is a funky plot because my outcome variable is not continuous and continues to have some violations of normality. So these are things that I would go through and say are going to be maybe things to think about. Okay, so I'm not concerned about nonlinearity. I'm going to take a look at a couple different graphs to determine normality at my distribution, and then thinking about homoscedasticity of my residuals. It's kind of hard to read from this plot because things are kind of wonky. Okay, so I'm going to move on from my leverage plot, my residual plot, and go up and take a look at a couple of different plots here. This is going to just be my histogram of my standardized residuals. And again, I was worried about potential non-normality in my residuals. Here, when I plot a histogram of my residuals, it looks all right. We do have some positive skew, right? Here's my mean, by definition, is going to be 0. We've got some slight evidence of some positive skew here, but it doesn't look like it's too terrible. Okay. Here is my PP plot. Again, we would expect for any variable that we look at this cumulative probability plot, if it's perfectly normal, it would fall right along this diagonal. We've got some S shape kind of going on here, suggesting possible positive kurtosis with this. But again, deviations don't look too terrible. So in terms of thinking about linearity of my residuals, my lowest line is doing some weird stuff, but I'm not terribly concerned about nonlinearity. Okay, so I'm going to say that's probably okay. Normality of my residuals, if I take a look at this, my distribution, my histogram, it's not perfect, but it's ish, probably okay. Probably something I don't need to be hugely concerned about, but I'm going to notice a little bit of positive skew here, and then homoscedasticity of my residuals. Don't know that we've got strong evidence of homoscedasticity, but I also don't know that I have strong evidence of problematic violations. Again, what we're seeing here is more an issue of the use of an outcome variable that's not a true continuous variable. Even with the transform, it's still skewed, still ordered categorical, and that's given us a kind of funky plot here. Okay, so this is going to go through and give us an assessment of our residual distributions. Other thing that we want to do is we want to now go through and take a look at our discrepancies, our leverages, and our influence values. Okay. So what I'm going to do is first I'm going to go through and I'm going to request, go to Analyze, go to Descriptive Statistics, get rid of this. And what I want to take a look at is I want to look at my studentized deleted residuals. Okay. And I'm going to hit, oops, actually here, I'm not, let's do this. Let's go, well, yeah, we'll do that just for the sake of being consistent with your handout here. I'm going to throw that back, and so we're going to have our studentized deleted residuals. I'm going to paste here, and then what I'm going to do is I'm going to go up and steal our examined, so you get our plots here. Okay. And here I'm going to say discrepancies. Okay. So first, I'm going to take a look at my output here. So my studentized deleted residuals. Remember that my studentized deleted residuals are going to be residuals that are looking at the difference between the expected value for a given case based on a model that doesn't contain that case, right? So if I have 200 people, or I guess 201 people in this sample, and I have Chris. Chris is in there. And what I'm going to do is I'm going to ask for, if Chris isn't in the model, what would be the expected value for Chris with him not in the model, and the deviation of that from Chris's actual value that we observed, right? And the idea is saying that how much of a deviation do we see from the model without that person versus if we had to include that person in. With our externally studentized residual values, remember that these are corresponding to or falling on a t-distribution with degrees of freedom equal to the number of the people in the sample minus the number of predictors minus 2, I think. Is that right? Yep. Number of people in the sample minus the number of predictors minus 2. Here we've got a large sample, about 200. These are functionally z-scores. So again, what we want to look at are things that are very, very large, similar to how we assessed our univariate outliers. And here, our minimum externally studentized residual is value of negative 2.2. Max is still under 3. So it doesn't look like we have any real big discrepancies that are going to be problematic, okay? But we want to go through and run a plots of these distributions just to see if there's anything weird going on. Whoops, forgot to change the outcome here. There we go. All right. So if I go through, and my residuals don't look too bad, right? There's nothing that's super large. So again, just under 3 is the max, just a little over negative 2 is the minimum. So nothing that's looking real terrible or huge here. In terms of my box plot, some large values, I got case 269. That looks like we are off in terms of predicting that score. Again, it looks like the observed score is larger than what the expected score is by quite a bit. That's going to be this case. So again, I might, think about, oh wow, what's going on there? But if I go through and I sort my studentized residuals, I just reverse that. So this is my largest value. So case 269, right? And so if I go through and I take a look, that I didn't ask for a value. So my observed value is a value of 3.93 for my role functioning variable. What I expected based on the model was a little bit less than that. So it's kind of large, but in the grand scheme of things, not anything that we're going to identify as problematic based on that max value of about 2.9. Okay. So in terms of our discrepancies, we're doing pretty good. We're not too concerned about being too far off, or the possibility of having a collection of cases that my model's not doing a decent job of accounting for. So we're going to leave that alone. Okay. Next thing we're going to do is we're going to go through and we're going to take a look at our leverages. Remember that our leverages, if our discrepancies are problems in Y space, right? Deviations or differences between my observed variable or my observed outcome and my expected outcome, leverages are going to give us deviations or strange cases in terms of X space, right? My leverages are going to be essentially my multivariate, my assessment of multivariate outliers. So what I'm going to do, I'm going to say, I'm looking at my leverages, and here I'm just going to do the same thing. I'm going to take this, paste this down, but this time what I'm going to look for is my leverages. So I'm going to say LAV1. Okay. So I'm going to do the same thing here. So here, just going to request descriptives of my leverage values. And here I see that my leverages have a minimum of 0.005, max of 0.05, let's say 7. Okay. Now remember that SPSS is different than Stata. SPSS gives me my centered leverages. Okay. Centered leverages and standard leverages are a little bit different. But what I'm looking for in terms of a rough cutoff point is a threshold 3 times the number of predictors in my model divided by the number of people in my sample. Here I've got 3 predictors, so 3 times 3 is 9. 9 divided by 201, 201 people in the sample, gives me a cut point of about 0.045. So if I want to use a rough guideline for what I'm going to start to maybe look at in terms of cases that are maybe starting to look like multivariate outliers, and say, okay, I might take a closer look at cases that are 0.05 and above. But do not use this as a hard and fast rule. What we want to do is we want to go through and take a look at our graphs too, because right now, if I'm looking at my maximum, if my threshold is 0.045, I've clearly got cases that exceed that, right? And if I go through and I take my leverages here and I sort descending, right, because I just want to look at my large leverages, I've got, I've got a total of, let's say 0.045. I've got 5 cases here that are exceeding what I might think about in terms of being problematic in terms of my leverages, right? But what I wouldn't do is just identify these as multivariate outliers and get rid of them. What I want to do is I want to take a look and see what's the distribution of these, what are these leverages looking like relative to the rest of the sample. So if I go through and I take a look, I can see, yeah, I've got a set that's kind of separated out. I've got a few cases here. It looks like 310, 221, 202, maybe, that are my 3 largest ones. Yep. Okay. And so, boy, you know, those 3 are kind of large. Then we've got other ones coming down here. So probably what I might do is I might say, what I'm going to do is I'm going to focus on these 2 ones here, or maybe these 3. So 310, 221, and 202, because these are ones that seem like, in terms of their leverages, they're a little bit higher from the rest. So we've identified these cases as possible multivariate outliers, right, based on their leverages. But what we don't want to do is just say, okay, these are our problematic values and just get rid of them. What we want to do is we want to go through and systematically take a look at and say, all right, what about these values are making them weird in X space? What specific variables are causing these to look like they might be weird combination of predictors? Okay, so what I'm going to do is, again, we borrowed this from Tabachnik and Vidal, a quick way to hijack regression to give us a sense for and help us more specifically identify what might be going on and why these cases may be coming up as problematic. So what I'm going to do is I'm going to create a variable called MV1. Okay, so what I've done is I've said I'm going to tell SPSS to compute a variable called MV1 and set that equal to 0. You take this and do it again. So I've got MV1, MV2, and MV3. Okay. And so if I go through and I run this, it's going to give me, whoops, we need zeros there. There we go. All right. Run those. All right. And so I've got, I've created 3 new variables. I got MV1, MV2, MV3. And what I'm going to do is I'm going to go through, and this is all, so I've got a column of zeros. What I'm going to do is I'm going to place a 1 to mark my 3 cases that are multivariate outliers. So here's 1 for multivariate 1, 2, 3. Okay, so MV1, identifies case 310 from the rest of the sample. Okay. MV2 identifies case 221 from the rest of the sample. MV3, 202 from the rest of the sample. Okay. And what I'm going to do then is I'm going to go through and I'm going to go to Analyze, Regression, Linear. Now, this isn't something that we would want to do for an actual real case, or if we were running an actual analysis. But what we can do is we can hijack regression to try and give me a sense for what's going on in or the variables that are causing problems. So I'm going to go to statistics. I'm going to turn off all this stuff because I don't need any of that. And I don't need any plots. And turn all that off. And I don't need it to save any more things. Go turn all that off. I think that should do it. So I'm going to go through, hit paste here. Oops. I don't need this scatter plot function here either. Okay, there we go. So we've got, put that there. And just so, regression, linear, plots. Okay. I don't know, for some reason it's still trying to give me a residual plot, but we'll get rid of that. So what we've got here is just a straight up regression looking at my regressing my indicator variable here on opiate use, pain, and PTSD. Okay. And so if I run this, what I can go down through and take a look, and it looks like the variables that are causing this to case number 310 to register as a multivariate outlier is a combination of low pain and high PTSD, right? So we go through, we take a look at these p-values, mostly low pain score. So we got negative pain score, positive PTSD score. And if I go back up to my syntax and I look at my, I'll go through, grab my descriptives of my predictors here. And I don't need to save that. Get rid of my skew kurtosis values. We see that for pain, I have a mean value of 4, PTSD a mean value of 50. If I go to case 310, I see my pain value for this person is 0.33, so that's way, way below the mean. For PTSD, I've got a score of 79. That's quite a bit above my mean here for the sample of 50. So what we've got causing this case, so this case, 310, had the largest leverage value, right? Had a leverage of 0.057. Remember that our threshold for identifying extreme value or large values was 0.045, so this is my biggest leverage. And if I go through and I look at my outcomes, right, this is, so this person out here, right out here. So I've identified this person as an odd case, and what seems to be going on is this person is an odd case because they've got a combination of a really low pain score and a really high PTSD score. Mostly pain is the driver, and we see that that pain score is really low with a really high PTSD or a fairly high PTSD score. And so the combination of low pain and high PTSD like this is kind of weird for this sample. So we would say that this person was flagged as a multivariate outlier based on a high leverage value due to low levels of pain, high levels of PTSD. Okay, so we've accounted for our first case, but we still have two other cases here, right? Remember that we've got our MV2 variable is identifying uniquely case 221. Okay, so what I can do is I can just take this same regression model But this time, I'm just going to change my outcome to MV2, and that's just going to tell me what's going on with this next case. Okay, so if I'm going to go through and I'm going to run that, looks like MV2, case number 221, predictors that are causing this to be weird, primarily just a PTSD score. Okay, now typically when we identifying high leverage values is generally going to be an issue with a strange combination of variables, but it looks like for this case, what's really causing it to be problematic is a really high PTSD score, again, because our coefficient is positive here, right? And again, if I look at this case, this person has a case value of PTSD at 111. The mean for the sample is 50, so it's over twice the mean for this sample. And so for this case, really high level of PTSD is primarily what's causing this case to get flagged as strange. Okay. And then finally, we got one more case we'll go through and explore here. Multivariate 3. Okay, and here we're looking at case 202. Try and figure out what's causing this to be problematic. And it looks like here we've got a high pain severity score a low pain severity score, got a negative coefficient, getting this one flagged. Again, my pain score is 0 here when the mean for the sample is 4. Okay, so I've got a really, this 221 identified as an exorbitantly high PTSD score, this one as a really low pain score, and so really 310 is the only one that's kind of coming up as a strange combination of variables in here. Okay, so what we would do is we would want to note these cases. Probably most 310 is kind of the most sort of notable one as cases that are potentially problematic in terms of being multivariate outliers, but again, something that we might want to follow up with further evaluation, want to go through and double check to make sure that these scores are correct, seeing if there's any concerns with the validity of reporting with this person, seeing whether or not this is someone who's part of the intended population of evaluation, and then maybe seeing, what does this solution look like if we run it with or without the person. If it doesn't make any difference in our overall results, then we're probably good. If we've got one person in here that's dramatically changing our output, that's when we start to get nervous. For these data, it's probably not going to be a big issue. I don't know that this case is that problematic, but something we definitely want to note. Okay, so that takes care of our leverages or multivariate outliers. Last thing we'll look at within this output is going to be our influence. Okay, remember that our influence statistics are going to be a combination of leverage and discrepancy, and what we're looking for here is our cooks. So if I go up, again, I'm going to ask to plot this stuff here, but this time instead of leverages, I'm going to request, my cooks value. Okay. So here, taking a look at Cook's D. Okay. Remember that our rule of thumb threshold for Cook's D is going to be 4 divided by the number of people in your sample minus the number of predictors minus 1. So if we got 4 divided by 201 minus 3 predictors minus 1, this gives us a threshold of about 0.02 for something that might be considered a large Cook's D, but our max here is 0.05. If our threshold is 0.02, our max is 0.05. This would suggest that there are cases that we might want to take a look at. Again, if I go through and I sort my cooks, I'm seeing a lot of scores. I've got 14, I got 14 cases that are going to exceed that recommended threshold of 0.02 for further evaluation. So again, this is why it's so important to go through and plot these to get a sense for what's going on, because otherwise, if I just start throwing things out because they exceed a threshold, I'm going to start losing a lot of my sample. I'm probably going to be throwing out people who I don't need to throw out. So if we go through and with our examine command, take a look and get a histogram and box plot here. Okay, so our Cook's distance is increasing. We got kind of a collection down here at the tail that's separate from the rest. Again, we got case 130, 402 that are kind of going to be my largest influence values, and then a bunch of stuff here, right? The problem is, what we don't want to do is we don't want to just go through and chop off cases and say, okay, these are all exceeding some semi-arbitrary threshold, and so these are gone. What we've got is a number of cases that look like they have the potential to influence my solution, but they're not super high up here. And remember, one of the things that we can do, so we've got a number of cases, maybe 130 and 402 that are maybe the ones we might want to sort of take the closest look at. But remember that, and stated as it's a little better than SPSS, but we can go through and start to put together some combination plots to start to say, okay, what combination, what variables are coming up as kind of the repeat offenders. And so what I'm going to do is I'm going to go to Graphs, in the Chart Builder, and I'm going to take my leverage values and put those in the x-axis. And what I'm going to do is I'm going to take my studentized deleted residuals and put those in my y's. Let's hit reset. Okay. That looked like it was going to do something weird. So studentized deleted in my y, centered leverage is in my x, and then I'm going to go through and paste that. Okay. So what I'm going to do here is this is going to give me my plot of my leverages, or my multivariate outliers and my discrepancies here. And what I'm looking for are cases that are going to fall kind of up in this upper corner or this lower corner down here. Okay. Now, I don't know that I have much going on in the way of things to be concerned about here. But it's hard to know because it's not getting labeled. So what I'm going to do is I'm going to run this again. And if I double click here, what I can do is then go to close that. Show data labels. Okay. And then I'm going to hit close. All right. So remember, and then let's see, blow this up. Okay, so this is our leverages and your studentized deleted residuals. Here, we're showing this is case number 44 and case number 106. Remember that these are position in your data set. This is not case number. So what we want to do, let's say if we wanted to say case number 44, I would go down through and find case 44. So this is 310, right? And 310 was one of those cases that had come up previously. That's 130. It was some up there in terms of our large discrepancy. Case 106. Right, this is 221, another case that came up, right? So, but really nothing looking like it's going to be terribly problematic. So something up here would be a very, very, very high leverage value in combination with a very high studentized deleted residual. This would be something with a high leverage and a very, very sort of negative, an extreme negative univariate, or excuse me, studentized deleted residual. If we had cases up here and down there, that would be primarily what we would be concerned about. But for the most part, this is looking like it's maybe A-okay. But just remember that these are not participant numbers. These are order numbers. If I go through and sort that, and then I run this again, there you go, elements, show data labels. Oops. All right. See, now this was 44, it's now 120. It's just because I reordered this. So just be careful as you're going through and taking a look at stuff. Okay, so what we're going to do up to this point, we're going to go through and flagged numbers. And so at this point, we've pretty much finished up with our residual analyses, the things that we're going to do. The last thing we want to be mindful of in terms of our screening is going to be multi-collinearity. Okay, so this is pretty quick and easy. I'm going to go down through and I'm going to go to correlate, new bivariate. And what I'm going to look at is I'm going to request correlations between pain, opiate use, PTSD, and not role functioning. That's those three, and then my natural log of role functioning. Okay, I'm going to paste that. Take a look here. What I'm seeing, things looking pretty much A-okay in terms of intercorrelation. So I'm seeing relatively strong correlation between my natural log of role functioning and pain, correlation between opiate use and PTSD, so that's not looking too bad. I've got a modest correlation between opiate use and pain severity, which makes some sense, but nothing here that would suggest correlations in excess of things that would be potentially problematic in terms of problems with multicollinearity. Again, rule of thumb or things about like correlations, bivariate correlations of 0.9, you should have like shut the whole model down. If you get anything within a 10-mile radius of 0.9, that would suggest that you're just basically measuring the same thing on multiple occasions. But here with our bivariate relations, nothing much to be concerned about. The only other thing that we might have some concerns with are going to be the possibility of combinations of variables, true multicollinearity that could go in. And so what we're going to do is we ran these already, but what we're going to do is we're going to go through and ask for, we'll run it again. So if we go back to our regression model that we ran for our residual analyses here, we had requested some collinearity diagnostics. I'll just repaste this down here. All right. So we go through and we rerun this. And again, what we're concerned about here is our collinearity diagnostics. Okay, we've got our tolerance and our variance inflation factor. Remember that our rule of thumb for this tolerance values less than 0.10, VIF greater than 10. Again, if you got anywhere near that, you would have had problems 10 miles back. But here, all our tolerance levels are looking very good. Our VIFs are looking fine, suggesting that consistent with what we're seeing here, there's no real combination of variables that's looking problematic. Okay, if we were to see concerns with our tolerance levels, we could go down here and look at our variance proportions, see what potential combinations of variables might be problematic. Remember here, what we're concerned about are eigenvalues that are very close to 0, a condition index that's 0.3 in excess of 30, and then variance proportions of multiple variance proportions greater than 0.5. Again, there's nothing going on here that would suggest any problems with multicollinearity, and so we're pretty good there. Okay, so what we've done is we've gone through and we've taken a look at plausibility missingness. We went through and we looked at univariate distributions. We looked at univariate extreme values in our univariate distributions, and then we're looking at our bivariate plots, looking at our bivariate plots for evidence of nonlinearity and violations of our homoscedasticity. Okay. Then we went and took a look at our residuals. With our residuals, we want to see that our residuals are normal, that our residuals are no nonlinearity in my residuals, that my residuals are normal, and that my don't have evidence of heteroscedasticity within my residuals. Then we looked at our discrepancies. This is going to be our magnitude of our residuals, so we didn't see anything there. We saw a couple leverage values. These are potential multivariate outliers that are going to be potentially large, and so we flagged a couple of cases there that might look like they could be problematic. Took a look at our influence, which is a combination of leverage and discrepancy, and found a couple of cases, well, actually several cases, that exceeded conventional benchmarks. But again, when we plotted these out, they didn't look like they were overly too difficult or maybe causing too much of a problem. And then we looked at our collinearity and saw that our collinearity, we don't have any evidence of problematic collinearity in this data. Okay, so if we go through and take a look at our write-up. This is a lot to keep track of, but using this structure, sort of going through accuracy, plausibility, no missing values, univariate distributions. You can go through, take a look at this, look at it carefully, but this is things that you've been doing previously. Extreme values, all that's looking A-okay. Bivariate associations, no evidence of nonlinearity in our scatter plot matrix, a little evidence of heteroscedasticity across my continuous variables. Looking at the distribution of my residuals, approximately normal, some evidence of positive skew. Residuals bifitted, no obvious nonlinearities, no strong evidence of heteroscedasticity, although we're noting that a regression on my ordinal dependent variable complicates the interpretation, makes it kind of ugly and difficult to see what's going on. Here we're talking about our discrepancies. Here covering our leverages. We identified 5 cases as centered leverages above our threshold. 3 of these we went through and took a look at. 310, this was our value, had a case had a long combination of low pain, high PTSD, but the other 2 were pretty much just extreme values on one variable. So we're going to say while cases exceeded benchmarks for additional inquiry, 3 highest levels primarily characterized by extreme scores on a single variable. So again, even 310, low pain, but then the high PTSD was kind of marginal in terms of something. So again, primarily univariate stuff. So we're going to keep them, continue to monitor. Cook's D, when we get to influence, a lot of cases, identifying 1, 2, 3, 4, 5 cases as the most influential here. But again, nothing that started to look like it could be problematic or were obviously problematic. Multicollinearity, that's looking okay. So recommendations, acceptable distributions in our predictors, roll functioning is ordinal, natural log transform, increase it, but it's still, we've got a level of measurement problem. Residuals look like it's not terrible. Some positive skew in my residuals that could result in some suppression of standard error, but not probably something we're going to be terribly considered or worried about. Some cases identified for sort of closer watch based on discrepancy, leverage, and influence. Nothing that was clear red flags, flashing, blinking lights. We want to go through, and if you wanted to, you could go through and run models with and without some of these cases, but from what we saw here, none of the things that came up are going to have a huge impact on the case. So despite reasonable adherence to statistical assumptions, measurement of role functioning is a discrete ordinal variable, and that's problematic. That's the big thing with these data. We're going to have some alternative models that can take into account categorical variables, particularly variables that have large disproportionate values at 0. If we were doing this for an actual paper, our outcome variable is our biggest problem. We should be using ordinal regression, zero inflated Poisson regressions, and some of those types of models, as opposed to a straight OLS regression. But in terms of our other stuff, things are looking okay. All right. So that does it. There's a lot to go through here. There's just a lot going on with these models. Hopefully this helps. We'll run through this in class as well. But use this as a reference. Let me know if you have questions, and we'll talk about this more in class.